Hi everyone, I am Shomoji Chatterjee and this is TLE Eliminators. Welcome to the post-contest discussion of today's Hello 2025 contest. This was the first contest of the year and I just hope that you all had a great contest. Okay, so before discussing anything further, let me just confirm once whether my screen is visible and am I audible or not?
Yes, sir.
પાયથન તો સિમ્પલી થઈ જાય સી ને સી પ્લસ પ્લસ માં કેવું છે ખબર હે તાર નીચે આખું કમાન્ડ લખવું પડશે ફાઇલ ને બિલ્ડ કરવા રન કરવાનું હોય.
Okay, so I am audible, right? Someone please confirm in the chat. Okay, sure. So I have given everyone has the permission to unmute yourselves. So if you find any doubt or if you feel that the explanation is unclear or maybe you require some one more extra dry run, then please unmute yourselves and you can tell me. Apart from that, I hope you will not disturb the class by unmuting unnecessarily. That's great, right? So this was the first contest of the year. Let's start with the problem A. Okay. So the problem says Meg's table. One day, the schoolboy Mark misbehaved, so the teacher Shasha called him to the whiteboard. Okay. Shasha gave Mark a table with n rows and m columns. His task is to arrange the numbers from 0 till nm minus 1 in the table. Each number must be used exactly once in such a way as to maximize the sum of megs across all rows and columns. Uh, this is just a formal description of what the statement says. We will understand what it says in more detail later. So it says that Shasha is not interested in how Mark arranges the numbers, so he only asks him to state one number, the maximum sum of mex across all rows and columns that can be achieved. Okay, and what is mex? Mex is the minimum excluded mex of a collection of integers, is the smallest non-negative integer x which does not occur in the collection C. Okay. Before discussing anything further, let me first explain what mex is. So basically, if you have a set of numbers, then mex of a set of numbers, suppose you have a set of numbers a1, a2, dot dot an, and suppose you need to find the mex of it, then the idea is simple, that you find the smallest number c greater than equal to 0 such that c is not present in this set. So c is not present in this set. For example, just for some sake of concreteness, mix of a set of numbers, say 1, 2, 2, and 4 would be simply 0, right? Because 0 is the smallest non-negative integer which is not present in this set. Similarly, the mix of a set of numbers, say 0, 1, 3, 3, and 5 would be 2, because 2 is again a number, is the smallest non-negative integer which is not present in the set. Because 0 is present, 1 is present, and then there's no 2 here. So that's the smallest non-negative integer which is not present, and hence the answer is 2. So I hope it is clear to everyone what mix is. Can I get a few quick confirmation in the chat? Uh, okay, great. So once it's clear what mix is, now let me just explain what the problem asked for. So this is what the problem asked for. The problem says that in the input, we will be given two integers. So the input of the problem will be two integers n and m. Great enough. Now, what we need to do is we have to basically create a grid. So here we have a grid. Let me confirm once what n and m meant. Okay, so n is the number of rows and m is the number of columns. Great. So here we have a grid with n being the number of rows. So we have n rows and there are m columns. Okay. So that's clear. So basically, this is this grid where there are n rows and then there are m columns. So this is what the question said. This is just an example. Now obviously since there are n rows and m columns, the size of the grid is simply nm, right? So since the size of the grid is nm, we can insert nm different numbers into the grid. Now the question says that this is the exact set of numbers which we need to insert from 0 to 1 till it goes to nm minus 1. You can quickly see and confirm that there are nm integers here, right? From 0 till nm minus 1, there are nm integers. You have to fill these nm integers into the grid such that every element occurs exactly once, and you have to do something. So this is the objective of the problem. So the question says that the task is to arrange these numbers in the table so that each number is used exactly once, in such a way so as to maximize the sum of mix across all rows and columns. That means that means the following. So this is the column number 1, right? So this column, like these set of values, would have some mix. Let me call that M1. Okay. Let me call them C1. So this represents the value for the column 1. Okay. Similarly, this set of numbers will again have some mix. Let me call this C2. Similarly, I have these CM values for the M columns. Just similarly, I had these CM values for the MX values for the columns. I also have the same stuff for row. That means that this first row values, if you look at this first row and you consider this as a set, you get some value R1, right? The max of this row is R1, similarly R2 here, and you get some N values, right? So we will get the max like this. And the question says, that is the objective. The objective of the problem is maximize the sum of all R and C values. So maximize C1 plus C2 plus dot 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 plus Cm plus R1 plus R2 plus dot 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 plus Rn. So this was the objective of the problem. So I think the problem statement is clear. We need to organize, or we need to rearrange the numbers from 0 till nm minus 1 in such a way in this grid so that this objective is satisfied. We are able to maximize this value. Okay, so is the problem clear? Anyone just confirm in the chat? Any doubt with the problem statement itself? Right. Okay. So now let us discuss the solution. So when I was thinking about this problem, what is most crucial in this problem is the position of 0. Why so? Think about this. So suppose I have the grid here. So this is a large grid of n cross m size. So there are n rows and m columns. And then this grid is divided into rows and columns in some way, which we are not very concerned about. But what I am actually concerned about is the position of 0. So suppose 0 is somewhere here. Now what is interesting is what would be the value? So can someone tell me what will be the value of the max of this row? Like let me call this R some k. What will be the max of this row? Uh, can anyone tell me in the chat?
0.
Great. Because now think about, so suppose this is the kth row where 0 is present. So this is the kth row. In all other rows, there is no 0, right? Because all elements appear exactly once. So in all other rows, there will be no 0. And that means if we take the max of this row, what would be the smallest non-negative integer that is not present in this row? That would be simply 0, right? So the max of this row would be simply 0. That means if I consider all these RK values, then apart from this row, all other values would be simply 0. That is clear. And I can't help with it. Like whatever be my way of rearranging numbers in this grid, I can never assign a positive value to those rows which does not contain a 0. That means apart from this RK value, all other elements will be 0 and I have no choice in it. This same observation actually applies to columns as well. Like what would be the max of this column? 0 again. The max of this column is 0. And similarly, the max of all these columns remain 0 itself. Why so? Because 0 is obviously not present in this column. 0 is only present in this columns. So that means, suppose this is the jth column. So I get some value Cj here. So this Rk would be something greater than 0. This Cj would be something greater than 0. And remaining all other terms will be 0. So that means my objective is, my new objective is to maximize Rk plus Cj. That means what is Rk? Rk is the max of that row. What is Rk? Let me write it down. Max of the row which contains 0. Which contains 0. And similarly, Cj is max of the column. I'm not writing it, but it's basically the max of the column which contains 0. And I want to maximize this quantity. That's great, right? Now here is one more beautiful observation. Just like 0 is very important, because just by identifying whether 0 lies, you can actually find max of most of the rows and most of the columns. Remember that even the position of 1 is important. Why so? Okay, think about this. Suppose 1 is not present in this row and this row. So suppose I rearrange the numbers in such a way that 1 is neither present in the row containing 0, it is not even present in the column containing 0. Then what will be my answer? Anyone, what would be the value of Rk plus Cj then? Okay, so someone said 2, and that's exactly correct. Why so? Because for all other rows, the answer would be 0. For this row, because 1 is not present in this row, the max of this row would be 1. Similarly, the max of the column would also be 1. So that means my answer would be 2. And I can never increase that value. That means if I decide, that means if I decide to not keep 1 in zeros row or column, then the answer is simple. Answer is 2. That means if I need to increase the value, since I need to maximize the value which I can get, I need to always put 1 in either zeros row or zeros column. Because if I do not put 1 in neither zeros row or zeros column, then I can never get a value more than 2. So I think that is clear. Okay. So now suppose I have this grid. There are few observations we made. Okay. So suppose this is my grid. And there are few observations I made. What are the observations? The first observation I made is that I have to put 0 somewhere and all other rows max value would be 0. Great. Now I have to put 1 somewhere in this row or in this column, because otherwise I cannot increase the value much. So suppose I put 1 in this row. Great. Now can anyone tell me what will be the max of this column? What will be the max of this column? Anyone in the chats? Great, it would be 1, because 1 is not present in this set of numbers, right? So if I put 1 here, the max of this column would be 1. Similarly, if I would have decided something opposite, like if I would have decided that, okay, I will put 1 here. So if I would have put 1 here, then the max of this row would be 1. That means out of the two terms I have RK and CJ, which I was interested in. So out of RK or CJ, one of these will be definitely 1. I'm sure. Like in the optimal case, one of these will be 1. In a suboptimal case, where you do not put 1 in the row or column, both these values will become 1, and that is bad. But in any other case, at least one of these values will be 1. Okay. So now suppose I decide that, okay, I will put 1 in the same row as 0. Okay. So suppose this is some row which contains 0, and I put 1 in this same row. Great. So I know that the max of this row, uh, just a second. Yes, so I know that the max of this row is the max of this column is 1. I can't help with it. What is the maximum max of this row I can get? Any idea? Max of this row, because I need to maximize the sum, right? This is 1 and I cannot increase this. What is the maximum max of the row I can get? Any idea? No, anyone who actually 2 is not a right answer, because what I can do is, in order to maximize the max, I need to ensure that all smaller values are present, right? So I will do something, that I will try plugging in all values from consecutive into this row itself. And I will try inserting all consecutive numbers in this row itself, so that the max of this row starts becoming greater and greater. Note that there is no point filling up this column with values, because 1 is not present in this row. Yeah, 1 is not present in this column. So even if you fill it with 2, 3 or something, the max of this column would remain 1 as it is. But this row is crucial. You have a 0 here, you have a 1 here. If you do not fill a 2 inside, then the max of this will be 2. But you want to maximize the max, right? So you will try filling all numbers consecutively into this row, so that you get maximum possible max. Great. So what is the maximum possible max you can get from here? Any idea? Like there are n rows, and then there are m columns, right? So here there are total of m integers. So there are m integers here. So what is the maximum max I can get? Correct, number of columns. So that means, what does that mean? That means if I decide, okay, just a second, some issue here. Yes, sorry for the disturbance. Okay, so that means there are m integers, right? So in the optimal case, it will be best to fill up this row with the values 0, 1, 2, 3, and dot with m minus 1, right? And in that case, what would be the max of this row? It would be simply m. And what would be the sum? And m for the contribution of this row, and 1 for the contribution of, from the column, and the maximum sum would be m plus 1. That means, what did we just find out? If if I try to keep if I try to keep 1 in same row as 0, maximum answer is m plus 1, right? So can someone guess, like, what would be, like, if I try to keep 1 in same column as uh, 1 in same column as 0, then what would be the maximum answer? Same 0. Then what would be the max answer? Okay, great. It would be n plus 1. An exact similar argument, like just here, if I try to do something like, okay, so if I try to do something that, okay, I've kept 0 here, I will keep 1 here. Then I have to I have keep 1 here. So I know that for this row I will get a contribution of 1 only. That means I need to fill this column with consecutive integers. And if I have to fill this column with consecutive integers, the most optimal would be to filling up it with 0, 1, 2, dot dot n minus 1, n minus 1. And in that case, the max I will get here is n. So an n for the contribution of the column and 1 for the contribution of the row, and the maximum answer is n plus 1. So that means we have just two greedy choices. One is that you keep 1 in the same row as 0, then we get n plus 1. And one is you keep 1 in the same column as 0, and in that case you get n plus 1. We have already seen that for all other cases, you can never exceed a value of 2. That means my final answer should be maximum of these two. So that's a max of n plus 1 and m plus 1. You can actually have a look at my code, and this is exactly what I have done. Like, I have taken n and m as input, and I've simply printed the maximum of n plus 1 and maximum of and m plus 1, which is simply maximum of n and m plus 1. Okay, so is the solution clear? Anyone with any doubts on the problem? Okay, can someone please confirm whether it's clear or not, like just one or two confirmations? Then we can proceed with the next problem. Okay, great. Okay, then I just assume that the explanation for the first problem is clear. So we can start with the next problem, right? Great. Okay, so let us start with the problem. The first statement is something which is not very relevant to the problem. Let's start from here. It says, for an array B, we define the function f of B as the smallest number of the following operations required to make the array B empty. Okay, so it says that for an array B, f of B is the smallest number of operations which is required to make the array B empty. Okay, what are the operations? Take two integers L and R such that L is less than equal to R, and let X be the minimum of these elements. Then remove all such Bi such that Bi equal to X from the array. Okay, and the question says, you are given an array A of length n and an integer k. No more than k times, you can choose any index I and any integer p and replace ai with p. Help the gorilla to determine the smallest value of f of a that can be achieved after such replacements. Okay. So just a second. Yes. So let me explain what does the problem asks for. The problem starts with discussing about a function. So here is a function f of a, where a is some array. Okay. So a is some array, and the function starts with starts with f of a. So what does f of a is? So the problem says that f of a is the minimum number of operations, the minimum number of operations required to make a empty. Okay. Now required to make a empty. So what are these operations? What are these actually? So the question says, in one operation, what you can do. So suppose you have this array of integers a1, a2 till an. You can pick any subarray. You can pick any subarray, say from L to R, and you can delete all the minimum elements of this array, of this subarray. So for example, just for the sake of some concreteness, suppose I have this array. I have a 7, then a 3, then a 3, then a 2, then a 1, then a 5. So what does an operation mean? Operation mean that you first choose some subarray. So suppose I choose this. So suppose suppose this is the subarray I choose. Now from this subarray, what is the minimum element of this subarray? The minimum element of this subarray is 2, right? You just delete the minimum element. So after one operation, the new array which you get is 7, 3, 3, 1, and 5. Great. Now you can again do the same, do some series, same set of operations. So you again make one operation. What does one operation mean? First, choose any subarray you want. So let me pick this subarray. So this is just one of the random or many subarrays you could have picked. So this is one subarray which I'm picking. What is the minimum element of this subarray? 1, right? So just delete 1. So after this operation, what is the length of the subarray? It's 7, 3, 3, and 5. Great. Now I can again make some operation. Now suppose I am bored and I make the operation on the entire array. The entire array is also a subarray, right? So I can make an entire operation on the entire array. The minimum element of this array is 3. So you basically delete the 3's. So after one more operation, you get the value 7 and 5. So let me write it down. So this is a new array, 7 and 5. You can make one, after you make one operation. So you understand that after every operation, the array becomes smaller and smaller, right? Because you are deleting stuff from the array. So that means after some finite number of operations, the array will become empty, right? Now you will understand what does this function mean. The function says that f of a is what is the minimum number of operations you can make to actually make a empty. Like we just saw here that for this array 7, 3, 3, 2, 1, 5, we made we made 4 operations and it was still not empty. Probably 1 or 2 more operations would have made it empty, right? So similarly, but in every operation, we randomly chose a subarray and deleted the minimum elements. Our choice of subarray dominates how many operations which we have taken, right? So we have to somehow optimally choose the operations in such a way so that the number of operations to make the array empty is minimized. So is everyone clear with the with what the function means? What is f of a actually for an array? Someone please confirm. Great. Okay. So what is f of a is clear. Now, now the question asks for something even more. The question says, let me read the question once again. The question says that you are given an array A of length n and an integer k, no more than k times. You can choose any index I and any integer p and replace ai with p. So this is what the question says. First of all, the question says that in input, you get a vector or you get an array which is say a1 till an, and you are also given an integer k. This integer k basically means that you have power to change k of these numbers to anything you wish. So suppose I have this, so basically I have this array a1, a2, dot 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 an. What I can do is I can pick any k of these numbers. So I can pick any k of these numbers and change to whatever I wish. So I can change it to some value p2, something I wish. And after this, I get a new array, right? So there are some values which remain unchanged. There are some values which remain changed, which become changed. So I get a new array. And the number of elements I have changed is less than equal to k. So after this, I have got a new array. And now I have to make such an array so that the value of f of this array is minimum. Right. And the question asks, what is the minimum value of f you can get? So you have an original array, you make some changes so that the minimum value, you achieve a minimum value of f, and you have to actually print that minimum value of f. So is the question clear? Anyone who has still doubts with what the question is? Okay, so the question is clear. Great. Now, there is one very interesting observation which I made. So first of all, forget about this. Like forget that you have K operations, and then you can actually make changes. These are things which we are of concerned, but we will later take care of it. First of all, let's think what is f of a. How to compute f of a? So I have been given an array A. How can I compute its f value? It's not that immediately clear, right? So suppose, for example, my A array is 7, 4, 1, 2, 5, 5, 7, and a 2. So what will be its f value? What will be, suppose this is my A array. What will be the f of a of this? So this is what I'm initially interested about. Okay, before me telling you the solution, can anyone guess what would be the f value for this array? Okay, I've seen some correct guesses. Okay, so there is one interesting observation about this operation. Don't you think that what we did, whenever we made the operation, we actually erased the minimum element of some subarray, right? But in one operation, can you ever delete two different values? Like is it possible that you made one operation and you deleted a 3 and a 7 at the same time? That is not possible, right? Because you choose a subarray. In that subarray, you have one unique minimum value and you delete that minimum value from the array. So suppose the minimum value is 1, you delete all the ones from the array, right? You never delete something which is not 1. So for example, like suppose I choose this subarray. What is the minimum value of this subarray? 5, right? So I delete all the 5s from the array. So that means I cannot delete multiple distinct elements in a single operation. So that means what is the minimum number of operations I will take? Like what is the number of distinct elements in this array? Number of distinct elements in A is in A equals you have 7, you have a 4, you have a 1, you have a 2, you have a 5. These are the 5 distinct elements I see. So number of distinct elements here is 5. Now, what my claim is that f of a is at least 5. Like f of a has to be something greater than equal to 5. I don't know what f of a is, but I claim that f of a is something greater than equal to 5. Why so? Because in one operation, like you would always need one operation to delete this one. Like in the same operation, you can't delete a 1 and 2 at the same time, right? So that means you will need at least one operation to delete all the ones. You will need at least one operation to delete all the twos. And similarly, for every distinct element in the array, you would need at least one operation. So that means the number of distinct elements in the array is actually a lower bound of the f value. Okay. So I think the lower bound is clear. So anyone doubtful about the lower bound? Okay, okay, great. So I know. So now the question is, can we match this lower bound? I know that the answer, can we match this lower bound? By this, what do I mean? I basically say that I know that for an array A, if there are d number of distinct values present, so d distinct values present, then I am sure, then I am sure that f of A is greater than equal to d. I have no doubts about this. But my question is, can we have a sequence of operations such that I can make the array empty in exactly d number of operations? If I can do that, then I can say that f of A is exactly equal to d. And we could say that, okay, we have matched the lower bound. So someone can give any hint, like what should be the sequence of operations? Like what should be the sequence of operations that to match this lower bound? Like I am sure that, okay, let me explain. So I am sure that I would need at least d number of operations to make the array empty. But it can be even more than d, right? What is the logical explanation? What is the formal proof behind claiming that, okay, that the f value of some array is exactly d? Basically, this is something like this, that you have some array, right? So something like this, that you have an array a1, a2, dot 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 an. In every operation, I can choose any subarray. So my idea is, why not choose the entire subarray? So why not choose this entire subarray and do the first operation? If I choose the entire subarray and do the first operation, I basically delete all the minimum values, right? So if I delete all the minimum values, I get a new array. Let me call this P1, P2, and some Pn dash, some lesser number of elements. But now what is the number? If I have d distinct values here, how many distinct values I have here? D minus 1, right? Now I can again make this operation on the entire array. So by doing this in every operation, I basically guarantee that the number of distinct elements decreases by 1. So in just D operations, by choosing the entire subarray at once and deleting all the minimum elements from the array, in just D operations, I can actually make the array empty. So again, going back to the like initial example. So suppose I have some examples 7, 3, 5, 3, and 2. What my claim is? My claim is that f of this array is number of distinct elements. Number of distinct elements in A, which is simply 1, 2, 3, and 4. It is 4. Now you will ask me, what is the set of operations which by which I can empty this in 4 operations? So this is something like this. 7, 3, 5, 3, 2. You make one operation. In one operation, what do? You take the entire array and you delete the minimum element. So now you get a newer array, 7, 3, 5, 3, right? Now again do the same thing. Take the entire array, erase the minimum element. You get a 7 and a 5, right? Again do the same thing. Take the entire array, erase the minimum element. You get you get 7. Again do the same thing. Take the entire array, erase the minimum element, and now you get something which is empty array. So that means in just 4 operations, 1, 2, 3, and 4, you basically reach the empty array. So that means f of a is exactly 4. So I think everyone is now convinced that f value for some array is nothing but the number of distinct elements in the array. Anyone with a doubt on this part? Can someone just confirm whether it is clear or not? Okay, great. So now everyone is convinced that the f value of some array is nothing but the number of distinct elements in the array. Great. Now, what does the initial question wanted for? The question asked, the question was that you basically need, what was the initial question? That you have some array a1, a2, and an. You have to change at most k places. So you have a power to change at most k, at most k indices, and you have to make the f value as less as possible. And we know f value is nothing but the number of distinct elements in the array, right? So you have to reduce the number of distinct elements to something as small as possible. So what should be a greedy strategy? So anyone can tell me what should be the strategy? Like I have k operations. What elements, what should I do? Like I know that f value is nothing but the number of distinct elements in the array. So my objective is to decrease the number of distinct elements in the array, right? So how can I do that? Like what elements should I exactly pick and replace to minimize the number of distinct elements in the array? Any idea? Any guesses? Uh, okay, correct. So let us start with some intuitive example. So suppose I have a 7, I have a 7, I have a 5, I have a 5, and I have a 5, I have a 3, I have a 2, and a 2. Suppose this is the array I have. Now, suppose I've asked that, okay, you have to reduce the number of distinct elements. So what should be the best element which I should pick and replace? So don't you think that the element which occurs the least number of times, it is best to erase that first and overwrite it with something else, like something which occurs large number of times, say 5. Using that, using only one operation, you reduced the number of distinct elements by 1, right? What again? Suppose you again have power. What should you do? You should pick that element which occurs least number of times. So now here comes 2. 2 occurs the least number of times, right? So that means try erasing these 2 and convert them to 5 again. So in two more operations, the number of distinct elements reduced again by 1. So what is the idea? This is the greedy strategy what we will follow. Let me write this. Greedy strategy. What I know is I have a power to change k numbers, right? So the greedy strategy is pick those numbers which have the least frequency with least frequency, destroy them and override them with the element which had the largest frequency, with the element which has largest frequency. So this idea works, right? Because if you pick those numbers which have the least frequency and destroy them first, then basically you take the minimum number of operations and you actually reduce the number of distinct elements by 1, right? Let me just show an example. So let us pick a test case from the CF problem statement itself. Okay, so this looks like a nice test case. So let me just pick it up. So here says n is 11. Uh, so let me write this test case. It says n is 11, k is 4. That means we have power to change 4 indices, right? And here is the array 3 2 1 4 4 3 4 2 1 3 3. So let me write this 3 2 1 4 4 and what, just a second, 3 2 1 4 4 3 4 2 1 3 3. Great. 3 4 2 1 3 3. Let me confirm finally. Yeah, this works fine. Now I have the power to change 4 elements, right? So let me pick those elements which have the minimum frequency. I see that, okay, 4 has a frequency of 3. There are 2, 4, and 1, 4 here. 3 has appeared a lot of times, 4 times. 1 has appeared 2 times, and 2 has only appeared 2 times. So that means let's pick 1 and delete them. So let's pick 1 and override them with something which has appeared a lot of times, say 3. So I have done it 2 times. So that means my power of k reduces from 4 to 2, right? I have 2 more operations left. So what to pick? The number which has appeared the least number of times in the array. So let's pick 2 and also overwrite it with the same element 3. So this also gone. Now if my k has reduced to 1, I can also pick this 2 and reduce it to something which has came the largest number of times in the array, and then this becomes 0. So what is the new array I have formed? I have formed 3, 3, 3, 4, 4, 3, 4, 3, 3, 3, and a 3, right? So by using these k equal to 4 operations, basically I've destroyed all occurrences of 1 and 2. So now I just have two distinct elements in the array. And I know this is the minimum possible f value, which is equal to the number of distinct elements in the array. So I know that the answer of this test case should be 2. So here it is. Okay, so is the idea clear? Like, is the solution clear? The solution is simple. You have a power to rewrite or overwrite k elements. Pick those which appear the least times in the array and overwrite them. Finally, you get something, some new array. The number of distinct elements in that array is the answer. Great. Okay, so let me just show you the code. Though I would suggest that you could always write your own code, and almost everything works. Like, the idea is simple. So I've taken n and k as input. I have taken the vector as input. I have made a map to store the frequency of every element, which I've done here. So fr I basically stores the frequency of the element I. Apart from that, I have also made a vector which stores these frequencies. Okay. Why I have done that? So that I can sort them up and I can pick those elements which have the least frequency first. So I've sorted the frequencies. After sorting the frequencies, I do a very simple thing. I just like iterate over that frequency array. If I find that, okay, the number of operations which I have k is greater than equal to the frequency, that means I can overwrite all those elements. I reduce my k with the frequency of those elements because I have used my power on those frequency of p elements, and I continue. And if I see that, okay, k is less than frequency of p, that means I cannot improve my answer again, and I break. So using this, so this was this p pointer which was increasing, and basically frec dot size minus p basically stores the number of distinct elements which remain finally in the array. I would not suggest you to follow this code 100%. Like, the idea should be clear, the solution which I explained here, and then I think it's very easy to code it up. So is it clear? So if someone of you have any doubts on this problem, please ask me. Otherwise, we will move to the next problem. Okay, how to sort according to frequencies. Okay, so the idea is very simple. Like, suppose you have this array, right? So suppose this array 7, 3, 4, 2, 3, 2, and a 4. And suppose you have one more 4 here. So what I did is I first made a map out of it. So I looked at this 7. Okay. So I looked at this 7. Okay, let me increase its frequency to 1. So this is a map which I'm storing. Then I go to 3. Okay. So I encountered a 3. Let me increase its frequency to 1. Now I encountered a 4. Let me increase its frequency by 1. Now I encountered a 2. Okay, let me increase the frequencies by 1. Then I saw 3 again. Okay, so let me override this 1 and write a 2 here. Then I saw 2 again. Okay, let me override this 1 and write a 2 here. Then I saw 4 again. Okay, so let me override this 1 and write a 2 here. I again saw a 4. So let me override this 2 and write a 3. So once I have iterated over the array, I have basically made a map where every element stores the frequency, right? Now I can simply create a vector out of this map. So this is what I have done. I have created a vector. I named it frec in my code, where I have stored all these frequencies. So I just push back all these frequencies from the map. So 1, 2, 3, 2, this is what the vector is. And then just simply sort it up. Just simply sort it. So now you have this 1, 2, 2, and 3. So this vector now contains all the frequencies in sorted order, and you can actually iterate over this array one by one to find the answer. So I hope it's clear. Okay, great. Just a second. Yeah, so I hope the explanation for this problem is clear. Someone confirm once, and then we will move to the next problem. Okay, great. So let's start with the third problem of the contest. This was my personal favorite for today's contest. The observation for this problem was quite a bit trickier, but then if you once observe a few important things after the problem becomes very simple. Okay, so let me read this problem. I am ignoring this paragraph. It was not something very relevant to the problem. So let's start from here. So it says that each pupil has an independence level expressed as an integer. In T generation, there is exactly one student with each independence levels from L to R inclusive. For a team of three pupils with independence levels A, B, and C, the value of their team independence is equal to A XOR B plus B XOR C plus A XOR C, where XOR denotes the bitwise XOR operation. Your task is to choose any trio of students with the maximum possible team independence. Okay, the problem statement was a bit messy, but the question asked for something very simple. The question basically gives you two integers L and R. Okay, and the question says that find three integers. So the question says something like this: find three integers A, B, and C such that all of them are, first of all of them are distinct. So A is not equal to B, B is not equal to C, A is not equal to C. This is the first condition. Everything should be distinct. The second condition is that you have to maximize. Okay, there is let me make this the third condition. There is a second condition, which is that all these A, B, and C should lie between L and R. So A should lie between L and R. Similarly with B and C, they should lie between L and R. So this was the second condition. And the third condition says that maximize the value A bitwise XOR B plus B bitwise XOR C plus C bitwise XOR A. So this was the problem statement. So is the problem statement clear? Someone please confirm once in the chat. The problem statement, okay, great. Now, if you look at the problem and if you read the constraints, it says that ln r actually lies from 0 till 2 to the power 30, right? So that means my ln r values can be of the order of 2 to the power 30. 2 to the power 30 is roughly 10 to the power 9. So this should give you a hint that, okay, looping over L and R will not work. So any solution which loops from L till R and try to find a solution will not work. Not even the brute force solution would have to iterate over three possible values A, B, and C. So that would definitely not work. But even looping once from L to R would actually give a TLE because 10 to the power because both L and R are of the order of 10 to the power 9. And usually in these problems, when the value of L and R is given, you usually need to observe the bit pattern in some fashion and try to understand what pattern the solution follows. Okay. So when I was solving this problem, uh, so these values of L and R can be arbitrary in the input, right? So let's forget about such complicated range of inputs which we can get and tell me a simple thing. Let's suppose this is the input. L is 0 and say R is something, say 1, 1. This is the binary representation. And suppose there are k ones. So suppose this is L and suppose this is R. What do you think the answer should be? So instead of basically thinking about a larger a range where L and R can be arbitrarily anything, let us start working on this simple input where L is 0 and R is all ones. And let us try to understand what the answer can be. But before discussing this, I want to discuss something else. I want to look at a stand for some time and carefully analyze what does this expression mean. A XOR B plus B XOR C plus A XOR C. For the sake of this problem, I am just assuming that you all know what bitwise XOR is. But just for a quick recap, when you have two equal elements, so 0 XOR 0 is 0, 1 XOR 1 is again 0, and for two different elements, 0 XOR 1 or 1 XOR 0, these values are 1, right? So that means what should be my objective? I need to maximize this value, right? So if I need to maximize this value, what value should I fit for A, B, and C? Note that here is something interesting. If if all A, B, and C are same, then this answer is simply 0, right? If all A, B, and C are same, then this answer is simply 0. Anyone? Okay, just a second. Yep. So what I said is that if all A, B, and C are same, then this A's or B, this B's or C, and this A's or C, all of these will become 0, and the answer would be 0. This is the first observation, that I should always try to make at least one different out of A, B, and C. If I have at least one different out of A, B, and C, then suppose A is 1, B is 1, and C is 0, then I will get A's or B is 0, B's or C is 1, and A's or C as 1. So in that case, I will get the sum 2. Note that you can never get something more than 2, because in any case, either if all the 3 bits are not same, then any 2 bits will be same and the third one will be different, right? So when you will make a XOR of these 2 bits, you will definitely get a 0. So you can never get something more than 2 if you're working on if A and B are binary values, right? Okay, great. So that means what should be the objective? That means the objective is the objective is make at least one bit different from others, right? So basically my idea is that we will try to understand or try to construct the solution bit by bit, and for every bit what will I do? I will simply try I will individually consider that bit, and I will try to make something so that out of A, B, and C, at least one of the bits is different and rest all are same. Okay. Uh, so let me, so now let us come back to the previous problem. Now you will understand slowly what is happening. So suppose L is this my binary representation. Suppose L is all zeros, and suppose R is all ones. Suppose this is the case. Now what will be the solution for this? What will be solution? Any guesses? Like what should be the solution if L is all zeros and R is all ones? Okay, let me explain the solution. Okay, so L and R are given. I need to find 3 values A, B, and C such that the objective A or B plus B or C plus A or C is maximum, right? And I have to also ensure that A, B, and C, these are all distinct values. So what can I do is, so let me first of all tell you the answer, and then we will try to understand why that is correct. So my objective is that if L is 0, all zeros, and R is all ones, then why not set A as 1 and then all these zeros. Set B as 0 and all ones. And set C as something. I just don't care. This is my idea. Now you will ask me why this is true. Okay, why this is true? First of all, realize that A and B, A, B, and C all lie inside this range, right? And I can set C as something which is different from both A and B. So A not equal to B, B not equal to C, that condition also remains valid. Now, why does this maximize the solution? Because if you carefully look at it, like A is 1 and then all zeros, B is 0 and then all ones, and C is something. C is say 0, 1, 0, 0, 1, 0, and 1, something like this. Now, if you try to analyze this situation bit by bit, consider this bit. In this bit, there is at least all three are not same, right? All three are not same. So that was what my initial objective was. When I was trying to explain this for single bits, what I said that if A, B, and C are all same, then that is bad. You will get something zero. In all other cases, it is good and it is optimal. So I will just try to construct my solution in such a way that all A, B, and C bits are not same. So look at here. I have always ensured that okay, A is 1 and then all zeros, B is 0, then all ones. So I've already ensured. So irrespective of what C is, I've already ensured that in every these position, the bits vary, right? So that means if you look bit by bit, in all these bits, there is at least one position which is different, and hence this is the optimal answer. Okay, so what is my argument? So my argument is that if L is all zeros, if R is all ones, then my optimal answer would be that you set A as 1 and then lots of zeros. You set B as 0 and then lots of ones. And then you set C as something in this range. It has to be in this range. So something in L to R, not equal to A and not equal to B. I hope you understand why this is an optimal solution. Because in an optimal solution, I need to and I have to analyze, or I have to ensure that at least one bit is different. And by just choosing this value of A and choosing this value of B, I have already smartly ensured that in every bit, I get at least one value which is different, because I always get a 0, 1 pair in all the bits. So anyone has a doubt why is this not optimal? Uh, okay, so is everyone clear? Like at least for this case, why that should be an answer? Uh, okay, great. So we have understood. Yeah, exactly. We will discuss this. Like, what if L and R's are not powers of two? How to handle everything? We will realize this. But this is the basic setup. This is the basic essence of the problem. You have to understand this case first, and the rest case actually comes just very simply. But you have to understand this, that okay, if L is something like L is 0 and R is some 2 to the power k minus 1, that is all bits are 1, then I can simply do something like this. I can set A as 1 and then all zeros. I can set B as 0 and then all ones. And I just don't care about C. You fit anything in C and it would give a maximum value. Because I've already ensured that in every bit, I at least get one thing different. Great. Now, let us look at the hard problem part of the problem. So say L is something. L is something weird looking binary. And suppose this is R. This is 0. This is 1. Suppose this is 0. This is okay. So R has to be greater than L, right? So I did an issue here. Just a second. Okay, so suppose this is 0. This is 1. This is 1. This is 1. Let me fill this up. And then this is something like this. So suppose this is L and this is R. I need to find what is A, B, and C, right? Such that this value is maximum. Now, the idea completely follows from our previous argument. Let me first tell you the answer. Once I tell you the answer, you will actually realize what happened. So I'm constructing three values. I'm constructing A, I'm constructing B, and I'm constructing C. Now look at the first bit. At the first bit, L is also 0, R is also 0. Now in this bit, you can't help but you have to put A, B, and C as the same value, right? Because if you put A somewhere in between A, B, and C, that will actually become outside the range of L and R. So that would be invalid. So that means in this bit, you have to put 0, 0, and 0 to all the three numbers. You just can't help. Now look at this bit. Same argument for this bit. You have to put 1, 1, and 1 at all these three positions. Why so? Because if you put a 0 somewhere here, then that would actually be outside the range L and R. So that would be an invalid answer. So now again go to this bit. Again 0 and 0 are same. So by the same argument, you have to fill this up with zeros. For these same two bits, you can't help but you have to do the same thing. Now here is where the magic comes. Look at this part of the problem. Here L and R, this is the first position where L and R are different, right? L has become 0, R has become 1. That means here you have freedom to put anything, right? So why not extend our previous solution to this? Like why not make L A as 1 and something something and all zeros here? Why not make B as 0 and all ones here? And C as C to be something. C can be arbitrarily anything, right? We just extended this previous solution and did it here. Like for all these initial bits, I had no choice. I had to fill in these values because otherwise it would exceed the, like it would just go out of the range LR, right? But here for the first time, for the first position where I see that, okay, the bits L and R differ, what I do, I just make A 1 and then all zeros. Note that this has to be in the range L and R because this 1 and then 0 and something is R. So A is surely less than equal to R. And because here there is a 0 and and A is here 1, so A is greater than equal to L as well. So A is less than equal to R and greater than equal to L as well. So that means A must be in this range. Similarly, by a similar argument, B is also in this range, right? And here I have ensured, just like the previous case, that if you take bit by bit, like see for these positions, I just can't help. I have to fill in those values because otherwise they will go outside the range LNR. After from this position, I have ensured that for all these bits, they are not same. At least one of them is different. Like that was the objective, right? And then you fill as C as something, just something which is in the range LNR and which is not A or B. So is the idea clear? Okay, there are few doubts. Why do we can't make that for 2 second bit? Why do they make? Okay, so let me explain it once again. So the idea is that suppose L is, so this is the idea that if L is something, say 0, 1, 0, 0, 1, 0, 1, 1, 0, and say R is some value which is 0, 1, 1, 0, 0, 1, 0, 0, 1. Then what should be my values for A, B, and C? What should A, B, and C be? My idea is that look here, like let's try to understand what bit we can fit here in A, B, and C. My claim is that you can't fit anything apart from 0 at this first position. Why? Because suppose I fit a 0 here, right? So instead of 0, if I try to fit 1 here, so suppose in B, instead of 0, I try to write a 1. If you try to write a 1 here, whatever you do in the rest of the bits, this value B will become greater than R, right? So this value B will not remain in the range L to R. So that is what I was saying, that in this first position, you can never fill a 1 somewhere here because then B would simply become outside the range. You have to actually put 0 in all these three positions. So this is the first argument. So that I have to put 0 in all these three positions. Great. So I just put 0 all here. For the next bit, the same argument holds. Why so? Like you have to put 1 at all these three places. You can't put a 0. Why I can't put a 0? Like suppose I erase this and suppose I put a 0 here. If you put a 0 here, look at L's bit. L was 1 here. And you put it and you actually inserted 0 at both places of B. That means B would simply become less than L, right? In this case also, B will not remain in the range L to R. So that means in order to ensure that these values A, B, and C lie in the range L to R, what you need to do, what you need to do, you need to basically ensure that the value is 1 again here. Now come at this bit. This bit is where the magic happens. This is the first bit where L and R differ. If you ever see a bit where L and R differ, what can you do? What you can simply write A as 1 and then all zeros. You can write B as 0 and then all ones. And C can be anything. C can be just anything. Because we have already seen that whatever binary you put here in C, in all the bits, at least one position will already differ because of how we have chosen A or B. So the choice of C does not matter. But is the choice of A and B clear? Uh, okay, this I will explain. Okay, so someone just asked, why are we not making all the bits same? So basically the idea is that if you look at one bit, so there is some bit one, like if you look at all the bit positions, suppose all the bits are same, 1, 1 and 1. So suppose A is 1, B is 1, C is 1. Then what is the value of A's or B plus B's or C plus C's or A? It's simply 0, right? Because A and B are 1, so A's or B is 0. Simply B's or C is 0. Simply C's or A is 0. So this will become 0. Similarly, if A, B and C are all zeros, then also due to the similar argument, all A, B and C will become 0. Apart from that, for all other arguments, you take A as 1, B as 0, and C as 1. Whatever you do, the value of A's or B plus B's or C plus C's or A will become 2. Why? Because A and C are 1. So this part will vanish up. This part will become 0 because they are the same. For rest of the part, you will get a contribution of 1 itself. And finally, you will get a value of 2. So what my claim is that whenever you are playing with binary numbers, don't think about large numbers. First, try to understand what happens when A, B, and C are 0 or 1. You get a greedy idea that, okay, A, B, and C can't be same. A and B has to be something different. Then you try to extend that same logic bit by bit on every bit position. So on every bit position, I will try to ensure that, okay, I have to keep the bits A and B to be something different. So here I have done a similar logic. For the first few bits, I cannot overwrite anything in A or B because in the first few bits, I have to ensure that, okay, A and B remain in this range. So I have to fit A with zeros. Then I have to fill A and B with ones because this bit is 1, right? But at the first position where I see that, okay, L and R differ, now I can play this magical idea. I can actually insert A with 1 and all zeros. I can insert B with 0 and all ones. This will first of all ensure that every bit has an alternating 0 and 1. So that is optimal. Apart from that, it also ensures that both A and B actually lie in the range L to R. You can actually look because if you look at A is surely greater than equal to L and less than equal to R, and a similar argument for B. And apart from that, once A and B are fixed, you can choose C to be anything you wish in the range L to R which does not match with A and B. Okay, so is the explanation clear? No, C can't be equal to either A or B. That is what the problem asked for. What value C can you choose? You can you can just loop over L and R. If you find a value which is neither A nor B, just print it and break it. So that should be clear. Okay. So anyone with any further doubt? Uh, okay, great. So let me just dry run on this. So someone shared a test case and asked for a dry run. So let me have a quick dry run on this test case. So he has shared some values of L and R. So let us have a look. Okay, so Sandipan says to keep L as 3031s and R as a 101010. Great. So let me keep L as 3 zeros and 3 ones and R as 101010. So nothing new here. You start from the first. Okay, just a second. So nothing new here. So let me write the values of A and B. So you look at the first bit. This is the first bit. L and R has referred already in the first place, right? That means you can simply put A as 1 and all zeros. And you can put B as 0 and all ones. And you are done. That basically the initial part where we were feeding same values of A and B is vacant here. So these values of A and B will work. What will C be then? What will C be? What you can actually do is how to find the value of C. You just loop over I equal to L to R. And then you say that, okay, if I is not equal to A and I is not equal to B, great, you have found your C. Just write C equal to I and break. Because C can be anything, right? We just do not care what values of C will be because we have chosen A and B optimally. So I hope it's clear. Okay, great. Let me get you through the code so that you will understand. So this is the code. I have first taken L and R as input, and then we have taken A, B, and C to be. We have initialized. We have just instantiated A, B, and C, and we will find the values. So I go from the most significant bit to the lowest significant bit. I extract the bits B1 and B2 of L and R. So look here. What is B1? B1 is nothing but the ith bit of L, and B2 is the ith bit of R. So if I ever see that B1 equals B2, what do I need to do? That if B1 is equal to B2, I just need to copy that bit to my answer, right? So that is what I've done. That I've copied that bit to the answer. Uh, so answer is basically B1 times 2 to the power I. And apart from that, whenever I find that, okay, B1 and B2 are something different, if B1 and B2 are something different, then I just plug in the values of A and B as something that I explained there, that A will be answer plus 2 to the power I and B is A minus 1. Okay, so you can actually look like what I'm doing every time is I'm filling A with 1 and then all zeros, and B with 0 and all ones. You can also observe that B is simply A minus 1. So these are just ways to write code, and almost you could have also iterated over all these bits and set these bits individually. That would also work. Anything is fine. Apart from that, once I have found the values of A and B, you just loop over L and R, and whenever you find a value which is not A or not B, you know you have got your C. Just get the value of C and break, and just print the values of A, B, and C. So is the idea clear? Anyone with any doubts on this problem? Okay. Okay, great. So now we will continue to the next problem. Just give me a minute. Uh, okay, so let's start with the next problem. Vivek is asking about something specific to your code. Vivek, I would suggest you to create a doubt and ask to the mentors, because without looking at the code, understanding or telling, resolving this doubt would not be possible. So let's start. We will discuss the problem E1 now. Actually, during the contest, I tried problem D for some time, and then I realized that, okay, probably I am not getting an idea. So I moved to E1 and I solved it. So let's discuss E1 for now. Okay, so E1 is actually interesting problem. I would just ask you all to hold your attention for some time, because there are a lot of nitty-gritty details involved in this problem. So let's start. The question says that you are given a connected weighted undirected graph with n vertices and m edges, which does not contain self loops or multiple edges. Uh, okay, just a second. Okay. So can anyone please confirm whether I'm visible or audible or not? Uh, okay, great. Thanks. Okay, so the question says that you are given a connected weighted undirected graph with n vertices and m edges, which does not contain self loops or multiple edges. Great. There are q queries of the form ABK. Among all paths from vertex A to vertex B, find the smallest kth maximum weight of edges on the path. Okay. Uh, Now the question says that let W1 to WH be the weights of all edges in a path in non-increasing order. The kth maximum weight of the edges on this path is WK. Great. So let me explain what does the problem say. So the problem says, so the problem here is the input. So the problem says that we are given a graph as input. So I've given a set of vertices and edges as input. Okay. So there is some graph which is given as input. So this may be some graph. There are some few properties of the graph which was said, which are pretty standard, and you can look at lot of so it is a connected graph. It is weighted and it is undirected, which does not contain self loops or multiple edges. So that means you will never find edges of this form from the same vertex to the same vertex. These are called self loops. These are not present. Apart from that, you will not have multiple edges between the same pair of vertices. These are multiple edges, which is not present. Apart from that, it has been said that every edge has some weight, say W1, W2, W3, and W4. And apart from that, there is only one connected component in the graph. So it is not that you have one connected component and then you have separate connected component like this. This is not possible because it has been said that the graph is connected. Okay. Now, what does the problem asks for? The problem asks for that you need to solve Q queries. So you need to solve Q queries. In every query, you will be given three integers, A, B, and K. What are A and B? A and B are simply vertices. And K is an integer. K is an integer, which I will explain what does that mean. So basically, in this query, what do you need to output? The question says that if you look from A to B in the graph, so this is some node A in the graph, and then there is some node B in the graph, and then there is some path from there can be many paths from A to B in a graph, right? So suppose there are multiple paths A to B in a graph. So these paths have lots of edges, right? So if I consider this path, suppose this path is of length t. So suppose this path is of length t. So this is A, this is B, and this is just one of the paths between A and B, and it is of length t. So it has some weight W1, W2, dot 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 WT. The question now suppose now the question says to reverse sort this. So basically you take this vector and reverse sort. So now you have a vector W such that W1 is greater than equal to W2, greater than equal to W3, and then you have WT. Pick the kth integer. Call this WK. So this is the kth integer. K is given a part of the query. This is where where K comes in the picture. So it says pick the kth integer. You get WK, and out of all these possible paths. So for all these possible paths, so here there are multiple paths, and for all these possible paths, you will basically get some value of WK, right? You have to actually print the minimum value of WK. You have to print the minimum value of WK in this query. So is the question clear? Okay, graph contains only one connected component means basically that from one node in the graph, you can actually go to any other node. So in like the graph is not separated. Like for example, consider this. Like suppose consider this. This is a valid graph, right? But it has two connected components. Like if you think about this is one connected component and this is one separate connected component. So this is a graph with two connected components. Similarly, if you think about this, then there is only one connected component because from one vertex, you can go to any other vertex, right? So this is a graph with a single connected component. So here the number of connected components is one. So that is how the number of connected components is calculated, and it is pretty standard. You can easily calculate it using DFS if you have studied graphs. Okay, so apart from this, is the question clear? Like what does the question asks for? Someone please confirm in the chats. Okay, great. So now we will try to understand this problem. There are a bit of details involved in this problem and a few ideas which probably there are some prerequisites required in the problem. So we'll try to understand this slowly. So first of all, in all these questions, the constraints on this problem is actually a good hint. So let us look at the constraints of this problem. It says that n is the number of vertices in the graph, is less than equal to 400. Apart from that, m, that is also the number of that is the number of edges in the graph, that is also less than equal to 400. And the number of queries is 3 times 10 to the power 5. Okay, so that means, okay, just a second. Okay, so that means that that the graph is quite small, right? Like the number of nodes and number of edges in the graph is just up to 400, but the number of queries is huge. Like probably you cannot do something very complicated in every query. In every query, you have to do something which is very optimal. But beforehand, before computing the queries, you can actually solve the problem quite like you can do some pre-computation and you can actually store information from the graph. Okay, great. Now, here is an idea. So what I was thinking about is when can I say, okay, so suppose I have some weight W and I want this W and I want that the kth weight on the path is less than equal to W. How can I check that? Any idea on how can I check that? Like basically, how can I find that whether there is a path between A and B such that the kth edge between A to B is less than equal to W? Okay, so here is the idea which I was trying to follow, and this is something like this. That suppose this is my graph. Okay, let us try to pick a test case and try to understand what is happening. So let me pick this test case. It says that n is 4 and m is 4 and the value of k is 2. Okay, just a second. Let me draw this graph. So there are 4 vertices. There is 1, 2, 3 and 4. Great. Now it says that the weight of 1 and 2 is 2. 2 and 4 is also 2. Great. So the weight of 1 and 2 is 2. The weight of 2 and 4, that is also 2. Apart from this, it says that 1 and 3 is 4, 3 and 4 is also 1. So 1 and 3 is 4 and 3, 4 is 1. Now let us try to understand what the queries are and try to understand what is the answer for each query. So this was the first query, 1, 4, 2. So it is basically asking, so this is the first query, let me call this Q1, and it is asking that from 1 till 4, what is the minimum second largest weight you can get, right? So basically here is 1, here is 4. There are many paths from 1 to 4, right? Like you can think like this is a path. So from 1 till 3 and then going to 4, this is a path. From 1 going to 2 and going to 4 is also a path. from 1 going to 2, then going back to 1, then again going to 2, and then coming to 4 is also a path. We have to consider all these paths. And from all these paths, I have to actually tell what is the second minimum value I can get. So what if I consider, let me consider a few paths. Okay. So here is the path from 1 going till 3 and then 4. What is the minimum answer I can get here? I can get an answer of 1, right? Because here this is 4 and this is 1. I need to pick the second largest weight. So that is 1. So for this path, my answer is 1. Similarly, I have a different path. I can go from 1 till 2 and then 4, right? So here the edge weight is 2 and here also the edge weight is 2. So I get a minimum of 2. The second largest weight is 2. So here is 2. Out of all these paths, you will realize that, okay, the minimum value is 1. So that you actually need to output. So the output is actually 1. So is it clear that what is the question asking for? Like the question asks that you have given two nodes and you have to compute, like for over all paths from the two nodes A and B, find the kth largest weight of all the paths and take the minimum of that. So is it clear what does the question asks for? Anyone please confirm in the chat. Okay, great. Now what I was trying to do here is like in every query, I have been given a start node, right? So I have been given a start node and then I have to, suppose I want this 1 as my answer. How can I check whether I can get 1 as my answer or not? If I need 1 as my answer, then I basically, okay, so for every query, so let me write it down in one query. Suppose my start node is A, so this is my start node, and my end node is B. This is also given, and I've been given an integer k. I have to iterate over all paths from A till B. So I have to iterate over all paths from A till B. For every path, I will take the kth largest weight. So for every path, I will take the kth largest weight, and out of these, I will take the minimum of them and output it. Okay. Okay. So how can I do that? So this was my initial idea, that why not construct a new graph? Let me construct a new graph. So suppose this is my node A, and suppose I have this node U1, and suppose I have this node U2. This is just for the sake of an example. Suppose this is some node U3, and suppose this is B, and this is B. And I need to find a path from A till B. There are many multiple paths I can get. Let me assign some weight to each of these paths. For an example, suppose this is 7, this is 4, this is 6, this is 8, this is 2, and this is 12. Great. So these are the weights I have assigned to this path, assigned to the edges. Now I need a path from A till B. Suppose K is given as 3, for example. Now I just want to check that, okay, can I have 4 as my answer? How will I get to understand that, okay, can I get 4 as my answer or not? If I want to get 4 as my answer, then I basically need a path from A till B which uses less than k edges with weight greater than equal to 4, right? Because what is happening? Because in some path, suppose I want 4 as my answer. That means, so here is the indices. There is 1, then 2, then 3. And in this, and this index, I need a 4 here, right? So that means I can use at most two edges which have weight greater than 4, right? So I can just use at most two edges which have greater than 4, and I have to actually reach from A till B. If I can use at most two edges greater than 4 and reach from A till B, then that means that I can actually give the answer as 4. I can actually achieve 4. So this is a way I can check that whether can I achieve some value x or not. If I need to achieve some value w in my query, so basically I have been given a query. So I have given two nodes a and b and I have given an integer k. And I need to check that, okay, can I achieve w? Can I have some path w? Can I have some path where the kth edge is w? In order to check this, I need to basically check that whether there exists a path from A till B such that the number of edges used with weight greater than W, number of edges used with weight greater than W is strictly greater than K. Because that would mean that, okay, I will fill the greater than W weights here, then I will have W here in the kth position, and in this way I can achieve W, right? So I just need to basically check that whether there exists a path which uses strictly less than k greater than w weight. Let me call these greater than w edges as bad edges. So it has to use at most k bad edges to reach from A till B. So is the idea clear? Like, why are we doing this? Anyone please confirm? Okay, I will repeat once again. So basically, I need to check. This is something like of a, so this is something like I need to check that, okay, can I achieve W? Like I want an answer, I want the minimum possible answer, right? Like basically there are some higher possible weights which I can achieve, and then there are lower possible weights which I cannot achieve. So I need to check whether can I achieve some value or not. So in order to achieve some value, suppose I need to achieve W. In order to achieve W, what I need to do is I need to find a path where W comes at the kth position, right? In order to find a path where W comes at the kth position, we need to actually use less than k edges which are bad. What are bad edges? Bad edges is something which have a weight greater than W. So we have to use less than k number of bad edges, which we can keep in the front, and after that W should come. If that is possible, then only we can basically have achieve W in my answer. So let me keep on explaining. After explaining a few things, probably it will get clear. So my idea is that, okay, I have been given some start node A and I have to reach B. So, and I have to reach from A till B and I have to check, does there exist a path? Does there exist a path which uses, does there exist a path which uses less than k bad edges? Just a second. So think about something that we are iterating over all weights W, right? So I have been given A and B, and now I need to find out that, okay, don't think about the time complexity much now. So suppose I have been given A and B, and now I need to check that, okay, whether some weight W is achievable or not. In order to check whether some weight W is achievable or not, what will I check? I will check whether there exists a path which uses less than k bad edges. What are bad edges? Bad edges are edges with weight greater than W. Okay, so any idea how can we solve this subproblem? Like we are given two nodes, A and B, and we need to check that whether there exists a path from A till B which uses at most k bad edges. Uh, any idea? Yes, I will explain the final approach. Let's try to understand it bit by bit. Then we will try to combine everything and get the final solution. Okay, so let me try. So basically, we are given two nodes A and B. We need to check we need to check whether there exists a path which uses at most k bad edges. And what is a bad edge? K bad edges. A bad edge means weight greater than W. Okay, great. So my idea is, why not construct, so I've been given the graph, right? So why not construct a new graph? So when I'm constructing the new graph, let me construct it in using such a manner that I will keep the vertex set same. So I will just copy the vertex set. And what will I make the edge set? So I will take all the edges, and I will assign them a new weight. So for every weight Wi, if I see that Wi is greater than W, then I will assign Wi as 1. Else, if Wi is less than equal to W, then I will assign Wi as 0. Let me explain this using an example. So suppose this is my A, suppose this is B, suppose this weight is 3 and you reach some node 1, then this is 4, you can have some node as 2, and this is 7, and this is 2, and this is 1. Okay, sorry for the mistake. These were the node numbers, so let me mark them as 3, 4, and 5. And these are the edges, so let me call these 6, 2, 4, and 1, and I have a 5 here. And suppose I ask that does there exist a path from A till B which uses less than 2 bad edges? And what is a bad edge? Suppose bad edges weight is greater than 3. If weight is greater than 3, I will call it a bad edge. So my idea is, why not make a new graph? So make a new graph using the same nodes. So when I'm making the new graph, I will use the same nodes. So I've made using the same nodes. And what I will do, that whenever I see a W greater than 3, I will mark its weight as 1. So this weight is 0, this is 1, this is 1, this is 1, this is 0, this is 1, and this is 0. Now, now I need to check, does there exist a path which uses less than 2 bad edges? And a simple idea to check is that I basically need to check that the minimum distance from A to B should be less than 2, right? Because whenever I use a bad edge, I actually give a weight of 1 to them. So in order to have a path from A to B which uses less than 2 bad edges, I basically need a path from A to B such that its sum of weights on that path is less than 2. So that means the minimum distance from A to B is less than 2. So that means here I can see that there is no path which uses less than 2 bad edges, because the minimum distance from A to B here is 2. So is this subroutine clear? Like how can you check that does there exist a path from A to B which uses less than W bad edges? So the idea is simple: make a new graph where all the weights, where the edge weight is 1, if it exceeds the threshold, else 0, and then you can find the minimum distance. So any idea on how can you find the minimum distance? Like in a graph where all the edge weights are either 0 or 1, what is the quickest possible way to find the minimum distance between two nodes? Anyone? Any algorithm which comes in mind? Okay. So basically, there is an algorithm which I will probably not explain here, which is known as 0-1 BFS. What does 0-1 BFS do? 0-1 BFS takes a node V and finds the minimum distance of V to all other nodes in the graph. So it finds minimum distance to all other nodes of the graph, to all other nodes when when the edge weights when edge weights belongs to 0-1. Okay. So you can actually use 0-1 BFS. So so if you have to check that whether there exists a path from A to B, you can actually make this auxiliary graph, and now you can do a simple BFS from A to B to check. Okay, whether to check that okay, does there exist a path with less than k bad edges? So you do 0-1 BFS from A, you get the minimum distance from B. Just check whether the minimum distance is less than k or not. Okay. So enough of subroutines. Now let me explain how does the solution work. Let's have a, yeah, Dijkstra would have also worked, but 0-1 BFS works in linear time, order n plus m time. Dijkstra works in some order m log n time, so n log m time. So that would be a bit of an extra time complexity, but that would have also worked. Okay, so here let's have a look at the code and we will slowly try to understand what happens. So basically, look here. We are reading the test cases. That's fine. We read the number of nodes, number of edges, and the number of queries in the in the graph. That's completely fine. Here there is a vector which stores the weights, and here there is where I store basically the graph or the adjacency list of the graph. Okay, so I am reading the edges. So I take U, V, and W as input. In the weights array, I basically push back all the weights and then I create the adjacency list. I hope this is clear. Now I sort all the weights in ascending order. I hope that's clear. Now I make a vector int of queries. So basically I read all the queries, and in reading the queries, I basically store it in this fashion so that basically I can basically remember that okay, which queries had actually started from A, and I have actually remembered that okay, what is the final target in how many what is the index number which is required, and this is which query number it is. Now here is what is the heart of the solution is. So let me explain what is happening here. So I am basically iterating over all the start nodes, then I'm iterating over all the weights. Now what I will try to do here, like since I've iterated over all, I'm iterating over some start node and then I'm iterating over weight, I will try to understand that, okay, can I can I have this weight as my answer? If so, I will get iterate over all the weights. I will check which weights I can have as my answer, and then I will take the minimum of them and output it. So what I've done, first of all, this part of the code is a standard 0-1 BFS code. I will not explain this. You can think about something like that. Okay, what I have done something like a BFS on a graph which has 0 or 1 weight, and I've computed the distance. So basically what I did, I iterated over every node. I iterated over all possible weights. So I fixed the weight and the node here. And then I did a 0-1 BFS from that node on the auxiliary graph. Okay. So what I did is something like this. So basically, I had this graph with n nodes, 1, 2, 3, 4, 5. Suppose these are the nodes, and then I have this weights array, right? So these are the weights array 10, 12, 6, 2, and 5. So suppose this is my weights array, 2, and I've sorted this weights array. So this is 2, 5, 6, 10, and 12. So I first fix a node. So I fix this node, say 3, and then I fix some edge weight. So suppose I've fixed this weight 6. So I fixed this node 3. I fixed the weight 6. And now I construct an auxiliary graph. How do I construct an auxiliary graph? Basically, I take this same graph. So let me redraw the graph. So I basically take the same graph, 1 here, 2 here, 3 here, 4 here, 5 here. In this iteration, we have chosen start as 3. We have chosen start as 3. We have chosen my weight as 6. So I construct my auxiliary graph. How do I construct my auxiliary graph? All the edge weights where I see are greater than 6, I mark them as 1. So this is 1, this is 1, and rest all are 0. So I mark this as 1, this as 1, and rest all are 0. And now what I do a 0, 1 BFS from here. So that computes the distance of this node from to all other nodes. So I basically compute the distance. So what is the distance from here? The distance from here is 0. The distance to 2 is also 0 because there is this path. The distance to 5 is also 0 because there is this path. The distance to 1 is 1 basically because you can choose a path which goes from 3 to 4 and then a 2 and then go back to 1. So distance to 1 is 1. So right. So basically this is what I did in this part of the code. So I have iterated over all start nodes. I have also fixed the weight, and then I have created an entire distance array. Right, I have done some 0, 1 BFS which basically populates this distance array. So now I have got the distance. Now look at what I have done. What I basically do is, like, I am iterating over the queries now. So I will try to answer all the queries which had started one of its positions. So how I am doing? I have stored the target, I have stored the max number of edges, and I have stored the query index. Now it is simple. If I know that the distance to the target is less than maximum number of edges, so every query gives me some maximum number of edges, right? So every query says that okay, there are you have to give w in the kth position. So what I have said that you have to since you have to fit w in the kth position, that means if you have to fit w in the kth position, that means you can use at most k. You can use at most k bad edges. You can use at most k edges which are of weight greater than w, right? And so basically in this iteration, this is what I have done. I have done 0, 1 BFS. So basically it stores what is the path from this starting node to some target which uses minimum number of bad edges. So if I see that the minimum number of bad edges which I use, which is basically stored in distance target, is less than the maximum number of edges, that means this weight W is achievable, right? So I say that, okay, this W is achievable. So my result is something minimum of this result. So I take the minimum of all those weights which are achievable and solve the problem. Finally, for every query, I've got the result and I print it. Okay, so this was the idea of the problem. I know you all may have some doubts. So you all can ask doubts which you have in the problem. The idea was something like that you need to iterate over all nodes, iterate over all weights, and then you check, okay, that for this node, for this starting position of the node, can this W answer be possible? So basically, if you see that, okay, this W is possible, then you try to take the minimum of it with the result. And finally, out of all those weights which were possible to achieve, you take the minimum of them. So is that clear? Someone please confirm in the chat. Okay, great. Uh, this question had some prerequisites. I would suggest you to read about 0, 1 BFS. 0, 1 BFS basically takes a graph where all the weights are 0 or 1 and then tries to find the minimum distance between, and it is similar to BFS. It takes a node and finds the distance from all other nodes. But in BFS, we work with unweighted graphs. So graphs where all the weights are 1. But here we can actually work with weights which are 0 or 1. You can actually also replace this code with a Dijkstra. Okay, great. So that's all for today. I hope all your doubts are resolved. Any feedback you have, you can fill the feedback form. That's all for today. Have a great night and have a great year ahead. Thank you.